Welcome to Allen High School Flipped Classroom for AP Chemistry as well as IBHL1 Chemistry. Now we're working at this point on reactions, double replacement reactions. These are ones that people have seen before in Chem 1, and we're reviewing them and then taking them to the level that the AP Chemistry testing requires. So let's do a quick review. This part should be review. We did go over this one in class, but let's emphasize a few things. We need to characterize or recognize what type of reaction we're dealing with. It's too much work, and I don't know how people would do it to memorize all the possibilities. So our goal is to look for patterns and trends of reactivity. And so when you come to reactions, one of the first things you want to do is determine what type of reaction you're dealing with. Now, it could be two ionic in this case. It could be an ionic and an acid, or an ionic and a base. Now, later on, we'll see acids with bases. And that is a subset of double replacement. And when we get into the acid-base unit in the spring semester, we will take a time to review and focus on the particular double replacement that involves neutralizing an acid or a base. Now, these are generalities, but when we come to these, typically one or even both are going to start out as soluble substances. Now, that doesn't have to be the case, but when it is, when they talk about soluble, often the word solution, or they'll say solutions of, to indicate that we're dealing with aqueous substances. Now, it's also possible that we have a gas, and they may use, in terms of the people that are writing the question, they may use the word bubbled through. So I took some chlorine gas, well, that wouldn't be a good example, a hydrogen sulfide, since it's double replacement, hydrogen sulfide gas, and bubbled it through the solution. There may be solids involved, and it may say solid, or you may see a word like crystals of. So those are some of the things you want to take a look at. Now, for a reaction to occur, we need a driving force. And that driving force will be the formation of a solid, a gas, or a molecular compound such as water. Not just water. We will also see that molecular compounds, things that don't ionize very much, such as weak acids or weak bases, could be part of that. But some molecular species that tends to stay in an undissociated state. Now, in double replacement, our oxidation numbers will remain unchanged. Now, for now, we're going to be focusing on ionic charge as if it's an oxidation number. But in Chem 1, hopefully you remember, and if you don't worry, I'll just tell you again. Oxidation number is a much bigger umbrella of terms than ionic charge, but ionic charge typically fits under that umbrella of oxidation numbers. Now, I want to take a look at that checklist that we had and see if we can unpack that a little better than what some of you are experiencing in your homework. So remember, we called it our old biddy. So remember me, your old biddy, Dr. Leggett, who loves you and works your bum off so you'll do a great job on this AP test. So biddy stands for balance, for B. D is dissociate, and I'll talk in just a minute. We'll unpack that term a little bit more. The second D is delete, and then decompose. Now, this is a great checklist, but you want to start seeking ways to streamline your work. I don't want to tell you how to do it initially. I'd like you to be working through the full processes that I'm going to be showing you, and eventually you'll need to find ways to get to that final answer much more quickly. Because our goal in an AP reaction, our goal is always going to be the net ionic equation. And we want to get there as quickly as possible. And I've taught you 3 full steps, but my hope is that very soon you won't need quite all of those steps. Now, let's first talk about this term dissociate. What do we mean by dissociate? What we want to do is take species that exist primarily as ions and break them into their ions. So here are the things that we do dissociate. We definitely want to dissociate our strong acids. And hopefully you've memorized those by now, or you're in the process of memorizing them as you work through these problems. We want to do our strong bases. Again, those are our group 1, group 2 hydroxides, except beryllium and magnesium. And these are assumed to be in water. Acids and bases are in the context of aqueous solutions, certainly at our level. And then we want to dissociate our aqueous salts. It's not just enough to say soluble salts. It's possible the question told you that it was a solid, and we're not going to be dissociating those. There are even times when you might see a quote-unquote insoluble salt, and they'll say that it's a saturated solution. So there may not be much of it in the solution, but there is still some present. You might come across that as well. But any word like solution or saturated, that would give you that indicator that we're dealing with an aqueous environment. At that point, we would dissociate into the constituent ions. Now, what don't you dissociate? Well, we don't want to dissociate our weak acids. So how do you know if it's weak? Well, basically, or effectively is a better word when talking about acids and bases. Effectively, if it's not one of your strong, you assume it's a weak acid. We aren't going to dissociate our weak bases. Now, our typical weak bases are centered on nitrogen. So a key example of this would be ammonia, or you may see it as a product forming as ammonia hydroxide, and I'll address that in a minute. But the key is that your solubility rules tell you it's aqueous, and indeed it is. It will be in solution, but you still do not dissociate it because it's a weak base. Now, we also won't dissociate solids, which is one of the reasons I carry that state all the way through the problem, even though AP does not require it. I carry it through. We won't dissociate gases, and we won't dissociate pure liquids or more molecular species. Water would be our key example of a pure liquid. We do not dissociate water. All right? Now, let's take a look then. Deleting spectator ions, we've talked about that, and I think that's best seen when we do it. Those will be ions that are identical on both sides of the equation. I want to take a look at that decompose again. You don't want to walk away from any type of reaction without addressing that decompose concept. And these are the three things that must be decomposed when they form as products. H2CO3 has to be brought to H2O and CO2. And you would see bubbles as evidence of a chemical reaction, as you would here. Ammonium hydroxide we write as ammonia and water, because that is actually a reversible reaction that lies very, very far towards the NH3 plus H2O. And you definitely smell that ammonia as an evidence of a chemical reaction. So those are the three that you want to keep in mind when you do that last step in the checklist. You want to decompose any product that anytime these three products form. Now, there's one other weird nuance in AP before I move into two examples for you, one of which will be a great help on your homework, because there's a very difficult one on your homework, and I've got one that models that. And that's when aqueous ammonia is listed as a reactant. Now, this is one of the few times that you can't simply put NH3 and then maybe slap an AQ after it. In this case, you have to supply the water as a reactant as well. Normally, if it says aqueous, we just say, it's soluble, we'll break it into ions or put it into water, however you want to deal with that substance. This time, you have to include the water. Now, to get the product of a double replacement, I think it's helpful to think of it. Do not write it this way or you will lose credit. Think of it as NH4OH because that's in essence how it reacts, as if it's an ammonium ion and a hydroxide ion. That's what the double replacement would be. The ammonium cation will go with the opposite anion, and the hydroxide anion will go with the opposite cation. So it reacts this way, so it's okay to think of it this way, but you have to write it as NH3 plus H2O as a reactant. So those are kind of the funky nuances as we get into these reactions, and I hope this little phrase will help you. The little Y in that is when you're all done, you can say, yes, I did it. And that's your old biddy. Now in the next video, I will do 2 examples for you, so I hope you stay tuned for those.